Hello, this is Sean Kelly. This is Earth 101, Introductory Astronomy. And we're going to be presenting material from Chapter 6 today. Just one moment. The stream is going to begin. All right. So Chapter 6 is all about the Earth and the Moon. And so we're going to talk about the special relationship. We have a really great moon, right? The moon is pretty important. It turns out that the moon has a bigger effect on the Earth than typical moons because its mass is much larger than typical moons are. So not the moon itself, the moon Ganymede of Jupiter is actually the largest moon in our solar system. But compared to its planet, our moon is the biggest moon and therefore has a very big impact on the Earth. So we're going to talk about the Earth and some of the evolution that we see happen. And the most important thing is to try to understand, why is the Earth alive? The Earth is alive. It's a planet that we can live on and survive because it's alive. Okay, and how does that happen? So the number one thing, how does the Earth live? The answer is because it's changing, right? So why is the Earth changing? What's going on? So we'll talk again about Earth and Moon being a system, the Earth and Moon together, right? We talked previously about the center of mass. The center of mass of the Earth and the Moon is orbiting the Sun. The Earth orbits the center of mass of the system, and the Moon orbits the center of mass of our system. The Earth it's the best place to live, right, in the entire solar system. It may not be the only place, though, and we're going to be finding out more about that as we explore our solar system. So here's just a comparison, right? You can look at the moons of Jupiter. Io, Europa, Ganymede, and Callisto. Ganymede is the largest moon in our solar system, and Callisto looks like it's the next largest, right? And if you look over there, Pluto is about the size of Callisto, maybe just a little smaller. Io and Europa are smaller. Our moon is slightly bigger than Io, I would say, and Earth is definitely bigger, but Jupiter, being so massive, is much more massive than its moons. So this is a big deal. So Pluto has a pretty big moon too, and we'll talk about that later. It's called Charon or Chiron. All right, so we're going to be talking about why the Earth is alive, and the answer is because it is hot inside. So I actually need you to know the reason the Earth is hot. Why is the Earth hot? And it turns out that there are actually 3 different sources of energy. And we want to be able to talk about qualitatively what they are. I'm going to go ahead and write them down right now. I think that maybe I should do this at this point. So what are the sources of heat energy the source of heat energy in the Earth? Sources of heat energy inside the Earth. And this is a little bit ahead of where what we've been talking about. But anyways, number 1, actually it's heat left over from its initial formation. And so we think that about half of the heat energy that the Earth has inside is about 50% left over from the initial formation of the Earth. So again, remember the concept of gravitational potential energy. The Earth is made of a bunch of pieces, right? But those pieces were once far apart. And when they fall together, that gravitational potential energy is converted into kinetic energy, which in turn becomes thermal energy. So this is the number 1 source of heat. A second source of heat we're going to learn is radioactive decay. And so radioactive decay is, it turns out, nearly 50%. Actually, I'm going to put down about 45%. Please don't quote me on these numbers exactly. They're just giving you like a rough idea. But about 45% would be radioactive decay, and we'll talk about how that works. And the third mechanism is the infall of oceanic crust. So what's really kind of cool is to realize that the oceanic crust is not going to be there forever. Oceanic crust is the crust beneath the oceans, and eventually it falls back into the Earth. And why would that be, and how does that happen? That's going to be part of what we talk about today. Okay, so the sources of heat energy, it adds up to 100%. A small fraction is from here. The rest, the other two pieces are the big pieces. Okay, so back to our slide set then. And we're talking about radioactivity at this point. And I actually have a couple of different things I want to talk about. Number one, what does the word radioactive mean? So radioactive atoms are atoms that are going to undergo decay. So the original atom is called the parent, and what it becomes is called the daughter. And that's actually a different element. So what does it mean? Why are some atoms radioactive? And the answer is they are unstable. So what I'm going to do actually is play with a little app that's actually pretty neat. It's called Build an Atom app, right? And let me see if I can find this now. I have to find this app. Pretty cool app. Build an Atom. Here we go. Okay, so we're going back to this new app. It's called Build an Atom. Okay, and what we're going to see is building an atom is pretty simple. How do you make an atom? So it turns out the first thing you need is at least one proton. And you can see right here that we have built the atom called hydrogen. And the reason is we put in one proton. And if you notice right here, it says positive ion. An ion is a word that you need to know. It's a charged atom. So if I put in one positive proton, I end up with a positive ion. If I want a neutral atom, then I need to put in one negative electron. So one negative electron plus one positive proton equals a total of 0. Okay, so you can make a neutral atom if you balance the protons and the neutrons. Protons and the electrons. Okay, so let's go ahead and try to add in a neutron. What happens then? So what we've done at this point is we've created a different isotope. So the word is isotope. And I'm going to go ahead and click this box right here. And I want you to notice, actually, let me take out the other one. This was stable. This was stable. Okay. This isotope is known as hydrogen-2 or deuterium. Okay, I'll write that down in just a moment. I'll write it on the paper and show you in just a second. So hydrogen-2, right? Hydrogen-2 or H2, and the name is deuterium. And at some point you need to know that. Okay, so deuterium is hydrogen-2. Now what happens if you and so it has a mass of 2 because that's one proton plus one neutron. That gives you the mass number. It's still element number 1 because it has only one proton. The number of protons is the atomic number. If I add a second neutron, then I form something unstable. And the word unstable here is the word radioactive. So hydrogen-3 is radioactive. It also has a name. It's called tritium. Okay, so it turns out that the number of neutrons can control the stability or instability of an atom. Now, if I add a second proton here, you see it's no longer hydrogen, it's the element helium, element number 2. And you'll notice that it's a positive ion. Well, again, if you have 2 protons, you're going to need 2 electrons to make it a neutral electron. What happens if you put too many electrons? Then you get a negative ion, right? So positive ions have fewer electrons than protons, and negative ions have more electrons than protons. And that's it, right? So if I hear you, if you hear about a positive ion, you know why it's positive. If you hear about a negative ion, you know why it's negative. Let's add another proton, and you see I've created something that's unstable. This is called lithium-5, right? I guess I should have done something more. I should have tried to make, there's unstable. Helium-5 is unstable. Okay, let's try lithium-5. Now lithium-5 is unstable, but lithium-6 is stable, right? So stability has to do with the number of protons and neutrons inside of the nucleus. And when we say unstable, what we mean by that is radioactive. So let's add another neutron. That's fine. Another one. Oh, now it's unstable again, right? So there's actually a region of stability when you have the right number of neutrons. You can go plus or minus 1 or 2 neutrons. It should be okay. But then at some point, too few or too many neutrons makes it unstable. Okay. Add another proton, and we get the element beryllium. And this current version is beryllium 8. But if I add a neutron, it becomes stable. Beryllium 9 is stable. How about beryllium 10? Nope, unstable again, right? So stability has to do with the number of protons and neutrons. This is boron, and one more makes carbon. That's very important. Carbon 11 is unstable. Carbon 12 is stable. How about carbon 13? Stable. And carbon 14, this is a very famous one, it is unstable, okay? So we're going to go ahead now and switch back to our regular thing. Go back to our slides. So these were the things that I wrote down for you. Hydrogen 2 called deuterium. Hydrogen 3 is called tritium. And then what did we say? Carbon 12 is stable. But carbon 14 is radioactive. So radioactive means unstable. Okay, so we're going to go ahead now and switch to a different app this time and talk about radioactivity. So this is, I'm going to go ahead and teach you how to use this. I put a link in Canvas for you, but make sure you press pause, okay? And then let's add a bunch of atoms, okay? So we've got a bunch of carbon 14s, and we just talked about the fact that this is unstable. So what's going to happen is that the carbon 14, which is the parent, is going to decay, right? It's undergoing radioactive decay, and it will become more stable. What does it become? It turns out this carbon 14 becomes nitrogen 14. So if you watch it, it turns out, I'm going to press play, watch how the carbon 14s change, okay? And you notice that they're not following a particular pattern. Oh, there's a couple that are holding on. Oh, there's one, just one left over holding on. Oh, it's gone. Okay. If you look, you can notice that there's no real pattern. And if I did it again, I'm going to find a different result, right? Because it's kind of random. It's not kind of random. It is random. It's probabilistic, okay? So it turns out it's kind of like flipping a coin. What do you get when you flip a coin? Do you get heads or tails? And the answer is, well, you can get either one, right? You don't know what you're going to get. And in the same way, a radioactive atom doesn't actually know when it's going to decay. It's kind of like every moment the atom is living as radioactive, it's asking the question, should I decay or am I going to stay, right? Should I stay or should I go now? All right, sorry, that's just a silly joke, never mind. But if you take a look right here, the more atoms you have, the more they behave in a very regular way. And so you want to write down this term right here, the half-life. The half-life for carbon 14 is about 6,000 years. The half-life represents the amount of time for probabilistically for half of the atoms to undergo decay, which means that half of them will become stable and the other half will remain unstable. Okay, so this is a pretty important idea. So the radioactive half-life represents the amount of time needed for half of radioactive material to undergo decay. So not everything decays at the same way. This is carbon 14, right? Carbon 14, we can have a whole bunch of them and we watch them decay. And again, right, what's happening? The amount of carbon 14 goes down and the amount of nitrogen 14 goes up. And at one half-life, you have exactly half of the carbon 14. At two half-lives, you have about 25% because half of a half. At three half-lives, you have half of a half of a half. It's about 1/8 or 12.5%. And the rest of it is always going to be the more stable version, okay? But not everything decays the same way. This is what's inside of the Earth. Uranium is inside of the Earth. This is the radioactive element that is heating the Earth. And uranium-238 decays into lead eventually. And so if you watch, right, this is actually going to be the decay. And you take a look right here, the time scale is very different. The half-life is about 4.6 billion years, right? So it takes 4.6 billion years for half of the radioactive uranium to decay, another 4.6 for half of that to decay, another 4.6 for half of that to decay, right? So anyways, this turns out to be a pretty neat thing for scientists. Here we are going to see something important. When you have anything that's living, including you or me, we are ingesting, as part of our living, carbon-14 as part of our atmosphere. And so we're getting carbon-14 in this. As long as we're alive, there's carbon-14. As soon as we die, the amount of carbon-14 begins to go away, right? It decays, right? As long as we're alive, it's maintained, and then it begins to decrease over time. If you measure the amount of carbon-14 in something, you can determine how long ago it died. Now, this only works if the thing was originally alive, right? Otherwise, things that are, were never alive will not have that carbon-14. The other thing you'll notice is that it only works out to maybe like 100,000 years, and maybe not even that far, because carbon-14 doesn't last as long, right? So it turns out after a while, this stops being very good. You need to use another isotope, another radioactive isotope. Now let's go ahead and switch to the rock here. And here we go. We're going to make a new rock, right? Oh, what was that guy? Where did he come from? Anyways, that was somebody being funny. And so here's the rock, and we're going to cool it off, and it's going to become a rock. And oh, we need to switch to uranium. Okay. So this time, instead of watching the carbon, we're going to watch the uranium. And over time, we'll see the uranium decrease. And the longer we wait, the less the amount of uranium will be left. So you can figure out how long ago this rock was created, came out of the earth, right? Okay. And the last one is just a game if you want to play it. It gives you a variety of things. We have rocks, and we have skulls and bones and fish bones and whatever, a piece of wood, a wooden cup, right? So here's how it works, right? We've got this wooden cup, and it tells you that there's 88.2% of the carbon-14. So what I'm going to do is slide this until I get about 88.2, and then I can go ahead and determine the age. And so pretty close to that. Oh, it's a little hard to slide. Okay, so you know what, 1,000, 1020, 1020 is my estimate. Oh, it gave me credit for that. Okay, so this is a pretty fun little game. Anything, and so something that's made of rock, you would not want to use the carbon-14 because there's nothing. You use uranium, and then you would go and figure out the age based on the uranium decay, right? 97.9. And you'll notice that this is millions of years, right? I got 130 million years. 130 million years, okay? And, oh, it didn't like that. Uh-oh, I got to do better than that. Okay, well, oh, 97.8, 150. Oh, I think I made a mistake. Let's try again. 153 million. 153 million. Okay, I wrote it out like that. Oh, that one I liked. Okay, so anyways, that is a cute little thing that you can do. Okay, so radioactivity works. Actually, let me go ahead and make sure you understand this. Radioactivity works according to the following idea. Whatever you start with, right, however much you have, you start with whatever it is, right? Let's say I start with 64 kilograms of carbon-14, okay? I have 64 kilograms, right? After I wait one half-life, and this is the symbol we use, one half-life, right? How much will we have? Well, we're gonna have half of this. We're gonna have 32 kilograms of carbon-14 still. Well, what happened to the other 32 kilograms? And the answer is, well, that's still there, but it's nitrogen 14, okay? So we still have 64 kilograms in all, but 32 kilograms is carbon and 32 kilograms is nitrogen. After you wait another half-life, same amount of time, right? This is about 6,000 years, another 6,000 years, right? How much of the carbon-14 do you have left? You have about 16 kilograms of carbon-14. And now you've got about, that 16 joins this one, and you have 48 kilograms of the nitrogen-14. Okay, still 64 in all. You wait another 6,000 years, another half-life, is the same amount of time every time. It doesn't matter that less of it is decaying, it's always half of whatever you have left, okay? So that's 8 kilograms left over, right? We can keep going like this. We're gonna stop right now. And then the other 8 goes into here, so we get 56 kilograms of nitrogen-14. So you can see that every half-life, half of whatever you have will decay. And so it takes a long time to get rid of all of it, okay? So we're still not done, right? We have 1/2, half of a half, 1/4, half of a half of a half, 1/8, right, etc. Okay. So that's the way radioactivity is doing. So when you have radioactive decay, you're going to release the energy into the earth, okay? All right. So here is a schematic of our Earth. You need to make a little picture, and let's talk a little bit about what you need to know. Okay, you need to know that the inner part of the Earth is called the core, and then the middle layer is called the mantle, and the very thin top layer is called the crust. But you also need to know a little more detail, right? The inner part of the core is solid, and the outer part is molten, meaning it can move, right? And it's really a combination of iron and nickel, okay? Now, if you look at this, you can see that it's about half the size of the Earth, right? Roughly half the size of the Earth. And so half of the Earth's diameter is an iron core, okay? Don't need to know all the numbers exactly because we don't know them exactly, but anyways. And then we have the mantle layer. The mantle layer is made of silicates, right? Remember silicates? We've talked about silicates, SiO2. That is the name for rocks on Earth, right? And we'll talk more about that. And then the crust is also made of mainly silicates with a little bit of water, right? And other things. But that's basically the structure of the Earth. Now take a look at the crust right here. It's 30 to 50 kilometers thick. It's tiny. It's just like a skin on the top layer of the Earth, whereas the mantle and the core are both, pretty significant, 3,000 kilometers right there. Okay, so here's an important idea. We've mentioned this before, that any molten body that separates into layers of different densities is said to have differentiated. So the Earth was large enough and hot enough when it was formed to differentiate. So we have the innermost part of the Earth, which is the iron core, is the highest density. And the outermost layer, the crust, is the lowest density, and the mantle is intermediate. So this is way too much information. I'm sorry, just let me try to focus on what's important. You do want to pay attention to this. Okay, there are actually 2 different kinds of crust, right? 2 different kinds of crust. That's actually a big deal. The crust is made of silicate, but different kinds of silicate, it turns out. So the oceanic crust is much thinner than the continental crust. The oceans, the greatest depth is about 7 miles or 11 kilometers. And if you might know where that is, that's the Mariana Trench. The mantle, again, is silicate. Blah, blah, blah. Yeah, the inner and outer core are both made of iron and nickel with some other stuff. And then the only thing that I think the most important thing left over is I want you to write down the temperature. The temperature of the inner core of the Earth is about 6,000 Kelvin. And what's interesting about that, we're going to learn later on when we talk about our sun, that happens to be about the same temperature as the surface of the sun. And I'd like you to know that, right? The core of the Earth is about the same temperature as the surface of the sun. And that's kind of a coincidence. Okay, so how does this layer get modified, right? These layers are going to be modified by something called plate tectonics. We'll talk about that. The mantle has convection in it, and then the outer core is going to generate our magnetic field. We'll talk more about that in a few minutes. Okay. So if you want to write down, continental crust is made of lower density silicates called granite. And you don't need the numbers, but I just wanted to write down for you some sample densities. These are called the densities, right? And the reason they're lower density is because they're made up of larger crystals. And it turns out that expands their volume, and therefore they have a lower density. So if you remember, density is the mass divided by the volume. We won't do any calculations with it, so it's just an idea. But higher density things will tend to sink, and lower density things will tend to float. So the oceanic crust is made of a higher density silicate called basalt. So those two words you need to know: granite or granitic, basalt or basaltic, right? And they're very different, right? So which one is more dense? Well, the average density of a basalt is more dense than granite. Oceanic crust is more dense than continental crust. You should know that. But the average density of the crust is less than the upper mantle, which is about 3.3 grams per cubic centimeter. So that's very interesting. Okay, so how do we know what's inside of the Earth? It turns out the answer is seismology, right? The study of earthquakes. So we studied earthquakes inside the Earth, and we figured out what the Earth looked like. And it's kind of an interesting story. You'll notice that there are different kinds of waves. There's the red ones, which are called the S waves, and these bluish ones, which are called the P waves, right? And yeah, let's talk about them. So actually, number one, you should know why they're called P wave and S waves, right? Why are they called P waves and S waves? I'll ask you that question and see if somebody knows. And the answer is P stands for primary waves. So if an earthquake occurs and you're over here, right, the P wave will get to you first and the S wave will come after it. So what does it mean? Which ones are faster? And you should know that P waves are faster than S waves. Now there's also something else going on. P waves are pressure waves, so they're called longitudinal waves. So the vibrations are back and forth along the direction of propagation, right? That's called a longitudinal wave. The S waves are shear, and they are also called transverse waves. So they wiggle back and forth like this as the wave propagates forward. And what's really interesting is we discovered that the P waves can go through the molten core of the Earth, but the S waves are completely stopped by it. They try to wiggle the molten core and they can't get through. It doesn't work. There's no shear strength. Okay? So this was actually how we discovered that the outer core of the Earth is actually a molten. Okay, so how does heat flow? This is an interesting idea, right? The inside of the Earth is hot, but it's actually trying to cool off, right? Everything is trying to cool off. And so you want to know there are three ways that things can cool off. One is called conduction. Conduction, when a hot thing touches a cold thing, heat will flow from the hot thing to the cold thing, and it depends on how different their temperatures are, and it depends on how much area they're touching, and it depends on their ability to conduct heat. Okay, so we're not covering any of this in the class. We're just an idea, right? So an example that people often give is if you stick a spoon, a nice cool spoon, inside of a cup of coffee or tea that's nice and hot, if you hold the handle of the spoon, after a while it gets warm. And it's not from you, it's actually coming from the coffee or the tea, right? It's conducting through the spoon. So the hot coffee is gonna make its way through the spoon to your fingers and deliver heat energy to your fingers that way. That's through conduction. Okay? Convection is when you have something carrying the heat energy, and that is called the convective fluid. So there's something that's hot, and it heats the convective fluid. The convective fluid will expand, and because it's less dense, will rise. For example, hot air rises, that's the convective fluid. And we'll find out that in the Earth, the mantle is convective. And so what happens is when the mantle material becomes hot, it expands and becomes lower density and rises. And it delivers its heat energy and contracts and gets more dense and falls back in. And the final is radiation, which we've talked about before. We're talking about black body radiation. Anything that has a temperature that's above absolute zero will glow with light, okay? All right, so here is our Earth. And let's take a look at this for a moment. I want you to remember again that the core is the surface temperature. I'm sorry, the temperature of the core is about 6,000 Kelvin, but that's the hot part, the hottest part of the Earth. So this inner core is touching the outer core and communicating and transmitting heat energy by conduction. The molten outer core is touching the lower end of the mantle. And so by conduction, heat energy is transmitted. But in the mantle, the conduction doesn't work very well. The material that's in here doesn't conduct heat energy as well. And so what it does is it absorbs the heat energy and expands and then begins to rise. And so what we see are these convective cells, which is the rising magma, the rising mantle material. And again, what happens, right? It's hot when it's here. As it rises and gets to the crustal plate, it's going to deliver its heat energy to the crust, and then it's going to become more dense, and so it's going to fall back down again. So you always get these cycles like this. So the crust is going to get the heat energy. Now what? Well, the crust has nobody to give it to, right? There's no one touching. There's no convection. I mean, you can do a little convection with the atmosphere. That's pretty small, though. If the Earth wants to get rid of heat energy, the only mechanism that it can do that with is radiation. And so the Earth is cooling off because of radiation, right? And everything in space, right, is actually going to cool off because of radiation. So they radiate energy, and the larger a body is, the longer it will take to cool off, okay? So interestingly enough, it's kind of cool that we actually know how fast the mantle is moving. It's moving very slowly, about 10 centimeters per year, right? This is very, very slow. But this movement of the mantle, we think, is what's pushing on the crust and causing the plates of the crust to move. And we call this plate tectonics. All right, so the Earth is alive, and we know that, right? There's a couple of big things. First of all, we see things like volcanoes and earthquakes. But we also see wind, waves, and rain, right? And so we have the process of building new structures, which is from the plate tectonics and volcanism. And then we also have the erosion from the atmosphere. Both mechanisms are changing the surface of the Earth and making it alive, right? The Earth is alive. So plate tectonics is relatively new. I think it's less than 100 years old. But a really wild idea is that we discovered that the plates are moving. And I actually, I realize now that I kind of forgot a little video clip that I want to show you. But we actually believe that all of the continents were once together, and that was called Pangea. So I actually want to try to see if I can find that real quickly because it's worth seeing. So here I am. I'm going to go ahead and show you how I'm finding it. I'm looking for, so we're looking for Pangea. Pangea, we want a little video clip. Let's find a little video clip. Here we go, a 1 minute video clip. That sounds good. 1 minute video clip, let's see. Where are we? Okay, so we're going to YouTube, hopefully. Oh. Okay. Oh, this is the future. Huh. Okay, well, that is not what I expected to find, but I actually really like that. But I think I want to show you guys the the past too, because that's actually here we go. Let's go ahead and try to find one more then. I'm going to go ahead and take this next one, 240 to 250 million years ago. So you might have noticed, if you look carefully, oh, this is way too long. Okay, 12 minutes. No, I don't want 12-minute video. But if you notice, I want you to see that actually look at how beautifully South America fits into Africa, right? And it turns out that we know this is true, right? That this is actually where they originally were. Because when we sample rocks on this part of South America and this part of Africa, they're identical to each other. So they were, in fact, at the same location sometime in the past. So this was known as Pangea. Okay, and then slowly over time, they have drifted apart. Okay, so I'm not going to be showing you the whole video, but I'll go ahead and post that link if you want to look at it. And back to here. Okay, so the plates are moving very slowly because of forces from the mantle. And there are going to be 5 different plate tectonic actions that you want to know about. Okay, so you want to make sure you know these. So number 1 is continental collision. And I actually think you should know at least one place where this is happening, right? So I'll go ahead and tell you where that's happening. The next one is subduction. And then we have spreading center. We have a hotspot, and we have transform fault, okay? So what is a continental collision? Well, continental collision is when 2 continental crusts smash into each other, right? They're going towards each other, and they have no place to go. So where do they go? And the answer is they go up. So it turns out right now, if we look at the Indian plate, it is smashing into the Eurasian plate, and the plates have nowhere to go because they're both continental crust, lower density continental crust, very thick continental crust. They are forming the Himalaya mountains, right? Mount Everest is one of those mountains. The tallest, craggiest mountains in the world are found right here. Now, what I find really interesting is that way, way back in the distant past, this happened right here on the eastern part of the United States. And actually, we know them now as the Appalachian Mountains, but they used to be incredibly tall. What happened to them? And the answer is they were very old, right? These are very old, so they have been weathered away. All the tallest mountains in the world will eventually be worn away. This takes time, okay? So the first one we said was continental collision. How about subduction? So here's an example I'd like you to know. Just off the western coast of South America, the Nazca plate, which is an oceanic crust, is pushing into the South American plate, which is a continental crust. And in subduction, the oceanic crust colliding with the continental crust, one goes up and one goes down. Which one goes down? And if you said oceanic crust, you'd be right. So the oceanic crust is going to ride underneath the continental crust. But what happens is you get a new mountain chain here. Okay, you don't have to know too much more about that. But one plate goes underneath the other plate. Oceanic goes underneath continental. Okay, that was subduction. And then we had a, let's see, hold on, spreading center. Okay, sorry about that. If you go to the Atlantic Ocean, right? It's supposed to be in the middle of the Atlantic. I don't see that here. All right, let me just show you this. This is an image of the mid-Atlantic ridge. And what's happening is that this oceanic crust is separating, right? These 2 pieces of crust are moving apart and they're leaving a gap. But nature doesn't like that gap. And so what happens? The magma from inside, from the mantle, flows up and fills the space. So this is the newest crust in the world. There is fresh crust that was made today, right? There's fresh crust that literally was made today from mantle flowing up to fill in the space. And the interesting thing is this, as these plates pull apart, this new crust will fill in the space and the oceanic crust gets bigger, right? So we're expanding the space and we're making crust to fill in that gap. Okay, and our next one is hotspot. And the hotspot actually is a kind of a weak part of the crust where the mantle material can flow up, and then it deposits in these flows. This is called a shield volcano. And anybody want to guess where this is? And maybe you said Hawaii. Okay, very good. This is Hawaii. And this is the latest volcano, but these are the ones that used to be growing, right? So as they get older, they wear down. And in fact, we can't even see them after a while. So the reason that you get a sequence of volcanoes is because the plate is moving. The hotspot doesn't move, okay? So hotspot is an example of tectonic plate that you need to know. And the last one is a transform fault. Okay, transform fault means one plate is sliding against another plate. And so the Pacific plate is actually sliding against the North American plate. Now, some people might have heard that California is going to fall into the ocean. Anybody ever hear that? And the funny thing is we already have, right? That's a joke, of course, because we're not ever going to. But in fact, Santa Barbara is part of the Pacific plate. We are not on the North American plate. And so we are sliding up past the American plate. This is called the transform fault. And what is happening on the transform fault? Well, that's exactly what you guys have heard about. I'm sure you've heard about the San Andreas Fault. So in California, this fault is a pretty major one for us to know about. And what happens is as the plates slide across each other, they stick and then they slip. And when they slip, you get an earthquake. All right, that was plate tectonics in just a few minutes. Okay, we're going to look at the Earth's atmosphere here, and you just want to kind of write down the names. You don't have to know too much. Definitely not the temperatures. Don't worry about that. But you want to know the names. So let's go ahead and start at the bottom. The troposphere. What do you see? I see a plane, and I see some clouds, right? So you want to know that this is actually where most of the water vapor is, and this is where most of the weathering is taking place, right? In the troposphere. So most of the action of our atmosphere is happening in the very lowest layer where we live. This is where we live. We live in the troposphere. Above the troposphere, maybe a little, 18 kilometers or 17 kilometers, up to about, looks like about 50 kilometers, we have the stratosphere. And the stratosphere is where we find ozone. And you need to know that ozone is a pretty important gas for human beings. One of the things that ozone does is it blocks most of the ultraviolet light coming from the sun. So we would actually have a bigger problem if we didn't have ozone. In fact, you might have heard that there's an ozone hole over Antarctica. And that actually, we found out that in the late 50s, early 60s, there was an ozone hole developing. And it was exactly because of chemicals that were being released into the atmosphere called chlorofluorocarbons. They were used in refrigerators and air conditioning. And when we discovered that they were damaging the ozone, scientists told the politicians, you've got to stop letting people use this. They have to stop using it, or else we're going to end up with no ozone or very big holes in the ozone. And so the laws were made that prohibited the use of these CFCs, and the ozone hole began to repair itself. And so it actually seems like it's going to be back to good as new. After about 50 years, it'll finally be back to good as new, which is good for us to know. Okay, science had a big impact on that one. Okay, so ozone, blocking ultraviolet from the sun. Next one up, mesosphere. So mesosphere, I don't have a whole lot to tell you. I see a bunch of streaks. That's where our meteors are going to leave their streaks behind. It's a very low density atmosphere. Yeah, that's about it. I think you can actually see little ice crystals sometimes. Okay, that's about it. And then above that, we have the very top layer, which is called the ionosphere. So you see the first word ion, and the thing that you want to know is that this is the electrically active part of the Earth's atmosphere. The ionosphere is electrically active. And so this is actually going to go out to the edge of space. So 100 kilometers is said to be, this is called the Kármán line, right? Or the von Karman line is the edge of space. If you go above 100 kilometers, you are an astronaut. And I hope all of you will be astronauts one day. So you've heard about it before. We want to know, what is this thing called the greenhouse effect? Is it a good thing or a bad thing? And a lot of times people, immediately say, oh, it's a bad thing. right? But what if I told you that the greenhouse effect is mostly a good thing, right? Without the greenhouse effect, we would actually be living on a giant snowball. And so we like the greenhouse effect. So I'm going to actually ask you to know greenhouse gases, right? What are the greenhouse gases? What's the most important one? And what are some of the other ones that we want to be aware of? I'm going to actually pause this for a moment. And I'm going to go back to here. And I'm going to ask you to write down the names of some greenhouse gases, okay? So greenhouse gases, what are they and how do they work? Well, we're about to get to that. So greenhouse gases, what are they? Well, the number one greenhouse gas, number one is water, H2O. So I don't know about you, but we actually don't really have any control over the amount of H2O, okay? Another one is methane, CH4. And then a third, this is the one that we're going to want to talk about, is carbon dioxide. So this is actually a really tiny part of our atmosphere, but it turns out that the human beings, we human beings, are changing that level. And that little change is enough to make a big difference. So this is our primary one, and this is good. These other ones, as they get added to the atmosphere, make the greenhouse effect more pronounced and are starting to cause some problems for us. So this is why we want to do something about it. So back to our slide. How does it work? What's the greenhouse effect? The greenhouse effect says that sunlight comes in, visible light, can pass through the atmosphere. But when it gets absorbed by the Earth, it will then try to come back out in the form of infrared light. And infrared light is blocked by the greenhouse gases. Okay, so CFCs, methane, ozone, nitrous oxide. These are other contributors, okay? So it turns out this is exactly like what happens in your car on a summer day. The light from the sun comes through your windshield because it's visible, and then it hits the seats, and then the seats get warm and they try to radiate, but they radiate in the infrared, and glass blocks infrared. And so the heat gets trapped inside. That's the greenhouse effect. So it's not that the greenhouse effect is a bad thing by itself. It is not a bad thing. It's that when we add on our extra carbon dioxide, it becomes too effective. And we're going to actually see, it's not from humans' fault, we don't think, but the planet Venus had a runaway greenhouse effect. And it's not something that we want to happen to the Earth, okay? We don't want that to happen to the Earth. This is just to be aware, again, we've talked about it, the global temperatures are going up, right? So every year is hotter than the year before. And so if you hear that in the news year after year, you start to get the feeling that there's a pattern, right? And it's pretty obvious to the scientists. This pattern is based on the levels of CO2 in the atmosphere. Okay, another not so sad thing is let's talk about the magnetic field of the Earth. The Earth magnetic field is a protective shield around the Earth. And you need to know a few things about this. Number one is, where does it come from? Why do we have a magnetic field? And so if you look at this picture right here, there's actually, this is wrong. Oops, this is totally wrong. Oops, okay. There's a north pole of the Earth and a south pole of the Earth. There's something wrong here, sorry about that. But anyways, we believe that the metallic core of the Earth is the way that we generate the magnetic field, called the dynamo effect. Let's call it the dynamo effect. Okay, but the thing is that it's not all of the core. It's just the molten outer core that is able to move. And so I'm going to show you a little simulation here that helps you to understand that, I hope. You might know a little bit about magnets. Here's a magnet right here. There's a magnet. And here's a thing called a compass, which is actually a miniature magnet. So you may notice that one end is red and one end is white, right? The red end is a north pole and the other end is a south pole, right? But why is it called the North Pole? Why is it called the South Pole? Well, I'm glad you asked. because on a compass needle, that end points towards the north, right? So if you look at this, you'll notice that the way this works is opposites attract and the same sign repels, right? So a north repels a north, but a north attracts a south, okay? So actually the very interesting thing you want to be aware of is that inside of the Earth, here's our Earth. In fact, the reason that a compass needle points north, right? Why does a compass needle point north? Is because inside of the Earth is a south magnetic pole. That's right. This is pretty crazy. But we didn't know this at first. We only knew that the compass needle points toward the north. Something's going on with our magnetic field right now. You probably have read about it, or some of you might have read about it. I'm not going to worry too much about it because it's still the dynamo effect, but it does change over time. In fact, we see evidence that the magnetic field flips every 20,000 years or so. And actually, you might ask, how do we know that? And the answer is it's recorded in the oceanic crust, right? Some of the material in the oceanic crust is metal, right? And the little metal pieces will actually align themselves with the current magnetic field. And when we analyze that crust, we find out that they're oriented in different directions, which is pretty crazy. Okay, so anyways, the North Pole of the Earth, right, where the North Pole, right, Santa lives up here, if you believe in Santa, at the North Pole of the Earth is a south magnetic pole. All right, so now how do you make it, right? And the answer is electricity. So this is a battery and it's making electricity. And so we have the flow, this is going to be the flow of electricity is going to make a magnetic field. And what happens is if you change the direction of the flow, you change the direction of the magnetic field, right? So somehow that's happening inside of the Earth, or something maybe a little more complicated than that. And that's what's causing the change. So the dynamo effect says that a circulation of charged particles, an electric current, generates a magnetic field. And this is the only mechanism I know for making big magnetic fields. It's the only way I know. So I know that the Earth has a magnetic field. I know that many of the other planets do as well. I know that the sun has a magnetic field. And when I ask you the question in the future, how do they generate magnetic field? The answer is the dynamo effect. Okay, make sure that you know that. So from the circulation of charged particles, we get a magnetic field. And so this is actually protecting us from the sun, it turns out, and from other stars, from other suns. So what happens actually is there's something called the solar wind. We've talked about the solar wind, right, when we talked about comets. But maybe I think I forgot to tell you, what is the solar wind made of? And I think today I want to make sure that I give you that information. The solar wind, go ahead and write this down. What is the solar wind made of? The solar wind is made of little charged particles, right? It's charged particles. And what kind of charged particles? Well, it turns out most of them, there's going to be maybe 3 major things, right, that are going to be the most common particles. So actually, the first one is a hydrogen nucleus. A hydrogen nucleus. Now, it turns out that hydrogen is element number 1. And so, in fact, the hydrogen nucleus is another name for a proton, right? A proton, actually, it's a positively charged proton. Remember, we said protons are positive. A hydrogen nucleus. So we've got lots of hydrogen nuclei flying out of the sun. Most common element in the universe, right? Most common element in the sun. Okay, but the second most common element, a helium nucleus. Okay, and that's a little bit different. I'm going to go ahead and write it down for you just because, I don't know why, just because I'm your teacher, okay? So helium, and you'll notice that it's positive too. It's positive 2, but it has another name. It's called an alpha particle. Please write that down because you're supposed to know what an alpha particle is. An alpha particle is a helium nucleus, Okay, it's a positively charged particle. And then the last most common particle that I want you to write down is the electron. And remember, electrons are negative. Okay, now this is not the only thing that's in there, but this is the bulk of it. Okay, most of the solar wind is this, this, and this. Okay, and probably lots of these, right, to compensate for all the positives. It's probably overall neutral, but anyways. So the solar wind is a pretty big deal. And yeah, all right, so there we go, solar wind. All right, I told you what the solar wind is. Okay, so now what, right? The solar wind comes in and tries to hit the Earth, but it gets to the magnetic field and something magical happens, right? The charged particles from the solar wind spiral around the magnetic field and they come down to where the magnetic field is strongest at the poles of the Earth. Some of them come down here and some of them come down here. And so we get this pretty amazing phenomena that you probably have heard about called the auroras, right? So I want you to know that there's actually two different kinds of auroras. They're called, actually, I'm going to go ahead and write it down for you. The aurora borealis, right? That's the northern lights. And aurora australis, the southern lights. And I haven't seen either one, but they are on my bucket list of things to see. So how do they work? These charged particles hit the magnetic field of the Earth, right? And they spiral around. And as they spiral around, they give their energy up to the air molecules, and the air begins to glow, right? This is kind of like the way meteors make the air glow too, right? But it's a much slower, a much more subtle effect, apparently. And I wonder if anybody here has seen the auroras, but I am so jealous if you have. I really, really, really want to go. But I do have a really cool video to share with you. I hope you'll watch this. This is a little video of the ISS, International Space Station, Aurora, okay? And so if I click on this, opens up a video, and you can't see it until I share with you. Hold on, there we go. And here is just a quick little video clip of the auroras taken from the International Space Station. And what an amazing sight this must be to see. I hope that some of you will get a chance to see this. Oh my gosh, this is like a dream. Look at that crazy color. Oh my gosh, so beautiful. Wow, that's even, I mean, I know it's amazing on Earth too, but that must be so amazing to see that from space. I can only imagine. So I hope some of you will get a chance to see that. Okay, so the auroras are coming as a result of the charged particles, the solar wind, interacting with the magnetic field. The magnetic field of the Earth is generated by the dynamo effect in the outer core, right? The molten outer core. And the reason we know that's happening is because iron is a good conductor of electricity, but the solid iron cannot conduct the way that the molten, that's not quite true, but the molten is where the layer that we're generating the magnetic field. Okay, just trust me on that. All right, so here we go. Another cool little thing that we want to talk about is the tides, right? High tide and low tide. And you probably already know the tides have something to do with the moon, right? But it turns out the sun is also part of it. It's a player. And so it turns out that the high tides are happening because of gravity, right? The high tides and the low tides happen because of gravity. So this is a little bit tricky. I'm actually going to go ahead and, you know what? I'm not going to worry about it too much. We're going to go ahead and just look at the picture here. This one's kind of obvious, right? This bulge is happening because the moon is pulling on this side of the Earth harder than on this side of the Earth, right? So the way it works is that because of that extra force, we get a bulge of water, right? And it has to come from somewhere. It comes from this part over here. We're looking down at the top of the Earth. This would be the North Pole right here. So this part is where the high tide is. This is where the low tide would be. Why does this high tide show up though? And the answer is because the force of gravity is weaker, this part of the Earth doesn't accelerate as much. And so the rest of the Earth kind of pulls away from it, leaving a bulge here. Anyways, no matter what you need to know, this is a key idea, what you need to know is that when there is a gravitational force between two bodies, right, there is a special thing that's happening. So let's go ahead and put the moon here and put the Earth, right? So the moon and the Earth. So which side of the Earth is closer? Well, this side is closer. So the force of gravity is stronger. And this part, the force of gravity is weaker. What does the moon do? In effect, it kind of stretches the Earth apart. And this stretching is called the tidal force. So you want to write that down. Tidal force, what is it? The difference in the force of gravity from the near side to the far side. Okay, so the tidal force of the moon on the Earth is the difference in the force of gravity from this side of the Earth to this side, and it stretches the Earth. Now the Earth also exerts a tidal force on the moon, but there's no water in the moon, so we can't see that. But we will learn in just a few minutes that it has had a pretty big impact. Okay, I'll tell you in a few minutes what that is. Okay, all right, back to, so tidal force, got that, okay. Stretching force. So a tidal bulge on the near side of the moon and on the far side of the moon. Now, it turns out they're not exactly lined up with the moon. And the reason is because the Earth is rotating. It pushes that lobe of water forward, but it's pretty close. Okay, now, the sun plays a role too, okay? But it is not as important as the moon. So if I ask you the question, how much tidal force does the sun exert on the Earth compared to the moon, the answer is about half as much tidal force, okay? Now, that's not the force of gravity, by the way. The force of gravity from the sun on the Earth is much greater than the force of gravity from the moon. But the tidal force from the moon is greater than the tidal force from the sun. Why would that be? And I hope you got the answer, because the moon is so close to the Earth, right? So it stretches the Earth more than the sun does. Okay, but we do want to understand what happens when the moon is either across from the sun, that's a full moon, or the moon is in the same direction as the sun, a new moon, is that the stretching of the moon and the stretching of the sun is along the same direction, like this. So both of these are going to be working together, right? The sun and the moon are working together to stretch the Earth. We call that a spring tide. Now, what's special about the spring tide? You get really high highs and really low lows, right? You get huge changes in the tides, right? You get high highs and low lows. Okay, so they're really extreme. So if you go to the beach near the full moon or near the new moon, you'll find out that the water is coming in and going out. And actually, we don't need to know the exact timings, but if you think about it, how far apart are the high tides from each other? And how many people said 12 hours? That would be a good guess, 12 hours apart. So how far apart is a high tide from the low tide that comes behind it? And the answer is about 6 hours, right? So in between, if you go from a high tide, about 6 hours later is going to be the low tide. And then 6 hours later is a high tide, right? So they come in cycles that are very predictable. There's a little there's changes that are slightly subtle. We're not going to worry too much about that. Okay, now let's look at the other side, right? What happens if the sun is here and the moon is here? Who wins? And the answer is the moon's tidal force is more important. So where is the high tide? And the answer is the high tide is going to be lined up with the moon. But the sun is doing its part, about half as big of an effect. So what happens? This high tide shrinks because it's being, some of the material is being pulled over to this way. So you get a low high tide and you get a high low tide. And what it means is that there's almost no variation in the tide. the water doesn't really go very far, right? And this is called a neap tide, right? So when the sun and the moon are working against each other, the ocean does not come rushing in and out like it does with the spring tide. It doesn't change much at all, okay? So when does this happen? We said the spring tide happens at a full moon and a new moon. When do you get a neap tide? And the answer is whether the moon is here, first quarter, or down here, third quarter. First and third quarter, you get the neap tide. So twice a month, right? Happens all the time. Now, it turns out that there is a little bit of a difference. The tide is not exactly lined up with the moon because the Earth is rotating this direction. It pushes the lobe of water forward a little bit, so it's just slightly ahead of the moon. And so the moon is being pulled forward by this, and the Earth is being pulled back by this. And so this is a very interesting thing that you want to be aware of. The Earth is being slowed down by this force. So I find it really incredible that we have some evidence of the growth of coral and a couple of other things, right, where we think we know how long a day was. But would you believe that 3 billion years ago, a day was only 12 hours? One rotation of the Earth was 12 hours, and today it's 24 hours, right? And this is what's happened, right? So if you remember, there's a principle called conservation of angular momentum. And this says what? That the angular momentum cannot be created or destroyed. And so what does it mean if the Earth is slowing down? And the answer is it is losing angular momentum. But I just said it can't lose. Well, yes, it can, as long as somebody else is gaining angular momentum. So as the Earth is losing angular momentum, can anybody figure out who must be gaining? And if you said the moon, you'd be correct. The moon is gaining angular momentum. And what's happening as a result of that is the moon is moving away from us. The moon is moving slowly away from it, very, very slowly, it turns out, just a few centimeters a year. So it's not a big thing, right? A couple inches, a few centimeters, I think, maybe 4 centimeters a year. A couple of inches max, right? Not even 2 inches per year. So it's a very slow change, but it is happening. So you do want to understand something. Is the moon rotating? And I posted a video for you. It's called synchronous rotation, but it's important that you understand that we can only see one side of the moon, right? How is that possible? So let's go ahead and take a look right here. We have a flag, right? An American flag, let's say, right? And we can see that flag. That's the face of this, that's the side of the moon that we can see. So there's a near side of the moon and a far side of the moon. Now, if it didn't rotate, right, the flag would be vertical and we would be seeing another part of the moon, right, if the flag didn't rotate. But the flag does rotate. When the moon goes 1/4 of the way around, the flag faces the Earth again, right? So the moon has rotated exactly 90 degrees. And when the moon has gone to this point, 180 degrees around its orbit, it is rotated 180 degrees. This is called synchronous rotation. And what does it mean? It means that the moon takes as long to make one rotation as it does to make one revolution. And that time is 27.3 days, right? So one rotation of the moon takes 27 days, right? 27.3 days. So we always see the same side of the moon. Now you might know that the Chinese have landed a rover on the far side of the moon, and it is actually roving around and analyzing samples. And it's the first rover that has ever soft landed on the backside of the moon, right? The far side of the moon. Okay, so this is a little image of the moon, and you can see it's got some blue areas and some red areas. And so the side that we see doesn't have as much red areas, right? There's a lot more red on the far side. And this is altitude, right? This is how high above the mean level. So these dark areas are lower lying areas. They're called the mare, okay? They're called the lowlands or the maria. A mare and maria is plural, okay? And then these reddish areas are called the highlands, okay? So you want to know those names. So we see craters all over the place. It turns out the youngest craters have rays coming out of them, those ejecta, right? And that happened much more recently. But we believe that the moon got hit by a lot of material about 4 billion years ago. It's called the late heavy bombardment. And so a significant amount of aging happened on the moon around that time. And in fact, we think maybe the formation of the Maria was in that area right then. So the heavily cratered parts are called the highlands. And so we have crater after crater after crater. But when you look at the dark areas, you find there's not very many craters there. Those are relatively young. And what does that mean? How did they form? When the late heavy bombardment occurred, we think that the impact cracked open the crust of the moon and allowed material to flow up and fill and pool. So they were originally valleys on the moon that filled in with magma, right, and became solid. So the Maria are younger than the areas around them, where we still see lots of craters. And this is actually a pattern that you want to know about. When you see smooth areas on a body with no craters, we know that it's younger because cratering happens everywhere, right? So if there's craters on one part of the moon, there should be craters all over the moon. But when you find a smooth area, what you know is that that area formed after the original moon formed. Okay, so the highlands are the reddish areas, right? This red, and the lowlands are the dark areas. So there's lots and lots of craters all over here and not so many craters in here, right? All right, so this is a little model of the moon. As you can see, it's got a core mantle crust, right? And there are no plates on the moon. There's one solid crust now. And the core is much smaller, but it's made of similar kinds of materials. And so this is actually the interesting question. Where did it come from, right? What is it? And we have a couple of ideas, and you want to know at least 2 of the wrong ideas and then 1 of the right ideas, right? So here's 2 wrong ideas. These are wrong, right? Just want to try to understand why they're wrong. But one is called the capture hypothesis. This says that the moon went flying past the early Earth and then was gravitationally captured, right? So I want you to write down something important. When a body gets captured, one of the things that we see are highly elliptical orbits. And I also want you to know that the moon has an almost perfectly circular orbit, really close to a circle. It is not very elliptical. So the number one thing I would tell you is that this really can't be captured because it's so circular. But there is something else that I want you to think about. If you could get rocks from the moon, and we have them, and compare them to the Earth, what would happen if it was captured? Would you expect them to be the same? And you would say, not at all, right? If it was captured, there's no reason for it to be the same. And therefore, you know, that's another good reason why the capture hypothesis is wrong. So don't fall for that, right? It can't be captured. Okay, here's another one. Remember I told you how the Earth was spinning faster, rotating faster when it was older? A long time ago, rather. 3 billion years ago, it was 12 hours, and it would have been even faster before that. Some people have said, well, what if a little blob of material again got flung off of the fast spinning Earth? That's called the fission hypothesis. So in that case, you would expect that the moon would be made of exactly the same stuff that we find at the surface of the Earth. And when we analyze the moon, we find out it's not like the surface, it's really like the whole Earth, right? It's got an iron core and it's got a silicate mantle, right? It's more like the Earth than just like the surface of the Earth. The surface of the Earth is much lower density silicate material and not very much metal, right? Very little metal compared to the core. But we, in fact, find a significant core in the moon. So this fails too. Okay, so this is just not right. So what is right? What's the right answer? And it turns out that the best answer we have right now is called the giant impact hypothesis. And in this hypothesis, a Mars-sized protoplanet, by the name, they give it a name, Theia, smashed into the Earth, and most of it was incorporated in the Earth, but a lot of debris was flung out into orbit around the Earth and then gradually coalesced until it formed the moon, okay? So the benefit is that you end up with a good fragment of Theia and Earth out in orbit, including metals and silicates, a good mixture. And that's what the moon truly is. And it has a beautiful circular orbit. So I did post a little link for you to take a look at a video clip of the formation of the moon. You can take a look at that. So that is chapter 6. So I think I am done for now, and I thank you for your attention. And oops, let's go ahead and I'll put this back on. Thank you for your attention. And we live in a wonderful world. Let's take care of it. And whenever you can, do the right thing. Take care of our Earth.